Hi and welcome to week 14 of the MathsTutor.ie Leaving Cert Ordinary Level 30-week countdown. So as always, the full 30-week countdown is available to all the full members on the MathsTutor.ie website. There's lots and lots of videos there and things to help you with your revision. This week we're going to be looking at arrangements and probability, so the start of probability. So we make a couple of videos available to everyone each week. So this week, the first video that we're going to make available is on the terminology, because there's a lot of new terms that come up when we're dealing with probability and arrangements and things like this. And you'll see that there's a couple of questions where they're going to ask us what we understand by something. So it's just important that we're all happy with the terminology and terms that we don't come across in other parts of the course, the Leaving Cert Ordinary Level Maths course. The second question, or the second video then, is a question from 2015 paper 2 question 1, and this is on arrangements. So one of the things we're going to be looking at today is arrangements, and this video will do a little bit more, so you can watch those after this lesson. So to get started then, what we're looking at is we're looking at arrangements. And when we're looking at arrangements, we're going to be using something called the fundamental principle of counting. So that's the fundamental principle of counting. And this is where we're going to be looking at how many ways can we do something. So when we're dealing with the fundamental principle of counting, we're going to be looking at how many ways we can do something. The second thing that we're going to want to see is when we're doing arrangements and looking at how many different ways of doing something, we're going to need to use a certain button on our calculator. So the button that we're going to need to use is this exclamation mark, and it's called factorial, and where we find it on our calculator is we find it here over the x to the minus 1. So you press shift and that x to the minus 1 button and you'll get your exclamation mark. So we would put in the number first. If I want 5 factorial and press equals, it'll give me 120 on my calculator. So what factorial means, so that's the factorial symbol. So that means taking that number and multiplying by all the numbers that come before it until I get down as far as 1. So I did 5 factorial. So 5 factorial means 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So when we're dealing with our arrangements, we're going to see that we have our fundamental principle of counting, which is going to be important of how many different ways can we do something. And we're also going to see this factorial button coming into play on our calculator, which is our little exclamation mark. So to have a look at a couple of questions then, the first thing we're coming across here, 2013 paper 2 question 1. So when we're dealing with probability, we'll often find it on paper 2. So Katie tossed a coin 200 times and threw 109 heads. Joe tossed the same coin 400 times and threw 238 heads. Lucy tossed the same coin 500 times and threw 291 heads. Katie, Joe and Lucy now think that the coin may be biased. So what we're coming across here is this terminology, and this is the first term that we're coming across, is this term biased. So when we describe something as biased, it means that it's not fair. So if something is fair, it means that all of our outcomes are equally likely, and we're able to look at it and say, well, this coin is fair. It means that the chance of getting a head is a half and the chance of getting a tail is a half. But when we're looking at this one here, they're deciding that this coin may be biased, which means that it may be not fair. So what we have to look at is we have to look at the actual probabilities that they're getting. So when we're talking about a probability of something, we either write it as a percentage, as a fraction, or as a decimal. So oftentimes in a question, it'll say, give your answer correct to 3 decimal places or something like that, telling me they want it as a decimal. If my calculator gives it to me as a fraction, I will often leave it as a fraction. And very rarely we will use a percentage. So we normally deal with fractions or decimals when we're dealing with our when we're dealing with our probability. So we're normally going to have our probability as a fraction or a decimal. So when I look at something like this, I'm going to take the first person here, who was Katie, and she threw the coin 200 times and she threw 109 heads. So she had 200 trials, and out of that, there were 109 heads. So for Katie, the probability of getting a head was 109 out of 200. So I've written it as a fraction, but when I write these as a fraction, I always see, can I tidy them up on my calculator? So 109 divided by 200, and that doesn't tidy up, but I could write it as a decimal as 0.545. Now, why I'm going to write these as decimals will become a little bit clearer when we look at why we think it might be biased. So that was Katie. The next one was Joe. So Joe threw the coin 400 times and threw 238 heads. So for Joe, the probability of getting a head was 238 out of 400. And again, we'll put that into our calculator. So 238 out of 400. And I get 119 out of 200. And I said I want to change these ones to decimals, so we'll change this to a decimal, so 0.595. And the last person then that we have is Lucy, and Lucy tossed the same coin 500 times and threw 291 heads. So Lucy, the probability of the head was 291 out of 500. So 291 out of 500, and that gives me 0.582. So we've worked out each probability. Now, it didn't ask me here, but out of these 3 people, which one of these answers is the most reliable, or which one would I think is the most accurate? So the more times that we carry out an experiment, the more accurate our answer is going to be. So Katie tossed it 200 times, Joe tossed it 400 times, and Lucy tossed it 500 times. So I would be expecting Lucy's answers to be the most accurate. But they've all tossed it lots and lots of times here. So they've all tossed it many times. So they're all going to give us a good indication towards whether this dice is fair or not, or whether this coin is fair or not. So if this was a fair coin, so that would be not biased, we would expect the probability of a head to be 1 out of 2 outcomes, or 0.5. So when I compared that 0.5 probability to 0.582, 0.595, and 0.545, I'm seeing that each of them got a higher probability of getting a head. So why they think the coin may be biased is that each got a higher probability of a head than 0.5, which is expected. Now, we're not guaranteed that it's going to be 0.5, so I could toss a fair coin 500 times and get 500 heads. It's just very, very, very unlikely. So the probability is very, very small that I would get 500 heads in a row. But when I look at this, I'm going to say each of these probabilities is greater than 0.5, which is what I would expect. So that's why they think it may be biased. For part B, it says Lucy uses all the data and calculates the best estimate of the probability of throwing a head with this coin is 0.58. Show how Lucy might have calculated this probability. So the overall best estimate of the probability of throwing a head would be the number of heads. So there were 109 and 238 and 291 over the total number of throws. So there were 200 and 400 and 500, and this gives 638 out of 1,100. And when that goes into the calculator, it tidies up to give this decimal, and they want it as a decimal this time, so 0.58. So that's how Lucy would get this data. So for part C then, Joe agrees with Lucy's estimate of 0.58 as the probability of throwing a head with this coin. He claims that the probability of throwing 3 successive heads with this coin, okay, so we've got first thing we're looking at there, 3 successive heads, is less than the probability of throwing 2 successive tails. Calculate the probability of each event and state whether Joe's claim is true or not. So with this biased coin, the probability of getting a head is 0.58. And when we're dealing with probabilities, the probability of all the outcomes has to add up to 1. So 0 is something that's impossible and 1 is something that's certain. And if we toss this coin, we're either going to get a head or a tail. So the probability of those two things add together to give us 1. So that means that we can work out the probability of getting a tail by subtracting the probability of a head from 1, which gives us 0.42. So 3 successive heads would be the probability of a head followed by another head followed by another head, and that means we're going to have to multiply that probability 3 times. So 0.58 by 0.58 by 0.58, and when we put that into the calculator we get 0.195 when we round it off. And the probability of getting 2 tails, so successive means in a row, is going to be 0.42 by 0.42. And when we put that into the calculator, we're going to get 0.176 when we round it off. So I rounded off both of these answers to 3 decimal places. So we can see here that the probability of getting 3 successive heads is 0.195, whereas the probability of 2 successive tails is 0.176. So I can see the probability of 3 heads is a bigger number than the probability of 2 tails. So that means that this outcome here of 3 heads is more likely to happen. So he's saying that it's less likely to happen. So we're going to disagree with Joe's claim. So Joe's claim is not true. Okay, so that's our introduction to probability. So just to give you an idea of how we calculate some probabilities and some of the terminology that we come across when we're dealing with probabilities. The next question we're going to look at is going to be about arrangements and our fundamental principle of counting. So this is 2020 paper 2 question 1. So it says a restaurant is offering a 3-course meal consisting of 1 starter, 1 main course and 1 dessert. There are 4 different starters, 3 different main courses, and 8 different desserts to choose from. So how many different 3-course meal combinations are available? So we have to write down the number of options that we have for each thing. So if we're going to have a 3-course meal, we're going to have a starter and a main course and a dessert. And to work out the total number of possibilities, when we write down the possibilities for each part of this 3-course meal, we then multiply by them. So we're going to say we have 4 different options for starter and 6 different options for main course and 8 different options for dessert. And when we multiply those 3 figures, we get 192 combinations possible. So sometimes when we're looking at combinations, if it's something small, like I have 2 options for the first thing and 3 options for the second thing, I can write out all the possible combinations. But here, when I have something with large numbers like 4 by 6 by 8, and they're not particularly big numbers, but it gives me a huge number of combinations. And you can see that you don't want to waste all your time answering this question by writing out all those combinations. So we use what's called the fundamental principle of counting. And this fundamental principle principle of counting tells me to take the number of options I have for each thing and multiply them. And part 2 is going to be from the fundamental principle of counting as well. So this says when Jack visits the restaurant, he discovers that the restaurant still has the 4 starters and the 6 main courses available, but is sold out of some of the desserts. Now, they're not telling us how many of the desserts are not available, so we're going to have to work that out. But now we know that Jack has 120 different 3-course meal combinations to choose from. So how many desserts are still available? So what we're going to look at is we're going to say the number of desserts is now going to be X. So we don't know what it was, but we had 8. It's definitely going to be less than that, but we're going to do exactly the same thing with our fundamental principle of counting. So we have a starter and a main course and a dessert, and we're going to multiply our options. So we still have 4 starters and we still have 6 main courses, but now we have X number of desserts because we don't know how many desserts we have. But we do know that the total number of options when we're doing this combination here with our fundamental principle of counting is going to be equal to 120. So we now end up with an equation in algebra. So 4 times 6 times x is 24x is equal to 120, and we divide both sides by 24, which gives us x is equal to 5. So that means there are 5 desserts still available. So that's an example of using our fundamental principle of counting, where we're going to see that we're just writing down how many options we have each time. The next part of question here is 2018 paper 2 question 3 part A, and this is going to be doing with our arrangements. So when we're dealing with our arrangements, it depends on whether we're using all of the options or only some of them, whether I'm going to be using that factorial exclamation mark or not. So with the first part of this question A, it says find the number of different arrangements that can be made using all of the letters. So that's my clue that I can use factorial. Each of the letters of the word rainbow, each letter is only used once. So there are 7 letters in the word rainbow. So that means when I go to pick my first option, so I'm going to put all these letters down in order, we have 7 different choices for the first letter. So I could put down any of the first 7 letters. And now we've used one of those letters. It might not be the R, so R is at the beginning at the moment, but we could pick any of those 7 letters. But once we've used one of them, we have 6 options left. And then we've used 2 of them, so we have 5, and then 4, and then 3, and then 2. And then when we've put down 6 letters, we'll only have 1 letter left. So we've only got 1 option for the last letter that we place, and that's the same as our 7 factorial that we saw at the start of this lesson. So when we're saying 7 multiplied by all the numbers that come after it down as far as 1, we could use our 7 factorial. And when we put that into our calculator, we're going to get an answer of 5,040. So we can use the factorial when there's 2 conditions. We're using all of the options and we're only using them once. So sometimes it will say no repetition allowed, which means I can't have or. I have to have different letters each time. Sometimes we will have repetition allowed, and when you're looking at that video, so the 2018 question that we're putting there into the comments for you to look at after this lesson, that one is an example of a password, and they do look at is repetition allowed or not. The second part of this question 3 part A is find the number of different 3-letter arrangements that can be made using the letters of the word rainbow, and each letter is used at most once. So that means again there's no repetition allowed here. We're only allowed to use them once, but we don't have to use all the letters because we're only using 3-letter arrangements this time. So we have 3-letter arrangements, which means that we're going to be choosing 3 of our letters. So when we're not using everything, we often draw boxes to fill in the number of options that we have. And like with our fundamental principle of counting, we're going to say multiply those number of options to get the total number of arrangements possible. So when I start with this, I have 7 letters and I can pick any of those letters to go into the first box. So we had 7 letters in the word rainbow, so we have 7 options to go into the first box. And like we had in our question A part 1, we've used one of those options, so now we only have 6 options for the next box. And now we've used 2 of our options, so we only have 5 options left. And then we're going to have 4, 3, 2, 1 unused. So we're going to have 4 letters not used because we're only using 3 of the letters. So this is not factorial because it doesn't go all the way down as far as by 3, by 2, by 1. It's just 7 multiplied by 6 multiplied by 5, and that gives 210 arrangements. So sometimes I'll be using all the letters and sometimes I'm only using some of the letters. And sometimes they're going to put restrictions on us. Now, it didn't ask in this question, but it could be asked. How many of the arrangements have the vowels together, each letter being used only once? So this is where we're going to be using all 7 of them, but we're going to put the vowels together. So the first thing is we're going to pick out what are the vowels. So we have an A and an I and an O. So our vowels are A, I, and O, and we're going to group those together. So they are now one thing that's going to move around with those 3 vowels stuck together. And we also have an OR, an N, a B, and a W. So in total, there are 5 things moving around. So we had 7 letters, but because we've grouped all the vowels together, we now actually only have 5 things. So when we did this question and we were looking at the beginning of it, we said we had 7 options to put down first. This time I only have 5 options. I could put down an or an N, or a B, or a W, or all of the vowels. So we only have 5 options for the first thing. And then we'll have used one of them, so we have 4 options, and then 3, and then 2, and then 1, which we know we can write as 5 factorial. The other thing that we have to take into account then is this group of vowels. So there are 3 things in here, and I wrote them down as A, I, O because that's the order that they came in the word rainbow. But when I look at this, they could be written as A-O-I or I-O-A or O-A-I. So I have to see, well, how many options do we have for those vowels? They're still together in all of these different options. So we do another set of. Now we're going to look at, so this was the 5 things. And now we're going to look at the 3 vowels. So the 3 vowels, when we arrange them, we have 3 options for the first one. It could be an A, an I, or an O. And then we've used one of them, so we have 2 options, and then we've only 1 left. And that's the same as 3 factorial. So now we have 5 factorial being multiplied by 3 factorial, and when we put that into the calculator, we get 720 different arrangements. So there were 5,040 different arrangements of all 7 of the letters, and out of that, 720 of those arrangements have the 3 vowels together. And you'll notice that when we're dealing with the fundamental principle of counting and when we're dealing with our arrangements, we're not writing it as a probability, it's not a fraction, it's not a decimal, it's not a percentage. We're actually just writing down how many different ways can we do something. Okay. So then we're going to go and look at a bit of probability again. So this is 2021 paper 2 question 1, and this says the game Twister is played using 2 spinners and a mat with coloured spots. The 2 spinners needed for the game are shown below. Both consist of 4 equal sections. The player spins both spinners and must then place their selected hand or foot on the selected colour spot in the game mat. The spinners below show the outcome of right hand on a yellow spot. So it tells me that there are 4 equal sections, and that's telling me that they're all equally likely. So on the second spinner, I'm equally likely to get a yellow or a red or a green or a blue. So there's no bias here. And on the first spinner, equally likely to get the left hand, the right hand, the right foot, or the left foot. So the first thing says, how many different possible outcomes are there in the game? So how many different possible outcomes? That's not a probability. It's asking me how many outcomes can there be. So that means I'm looking at a fundamental principle of counting. So there are 4 options on the first disc, and there are 4 options on the second, which means that there are 16 different outcomes. And that's all that I have to do to work out how many different options are there. Now, this is the size of the box that was given on this Leaving Cert question, because they were giving you the possibility that you could write out left foot blue, left foot green, left foot yellow, left foot red, right foot blue, right foot green, and so on, and list all your possible outcomes. But it's much quicker to use the fundamental principle of counting there and just give how many outcomes there are. So then we have a probability. So Kate spins each spinner once. What is the probability? So now we're being asked what is the probability. So now I'm looking for a fraction or a decimal or percentage. So what is the probability that she must use her left foot? So the probability of left foot, that's our first spinner. So when we look at our first spinner, there were 4 possible outcomes and left foot is one of them. So that means that we're just going to say 1 out of the 4 outcomes. Now, we could also look at all the possibilities that we have up here, but we didn't list them all. So if we had listed them, we would have had left hand yellow, left hand red, left hand blue, left hand green, right hand yellow, right hand red, and so on, and we would have 16 of them. And the question asks, what's the probability that she needs to use her left foot? So we would have had left foot green, left foot red, left foot blue, and left foot yellow. And we would see that 4 out of the 16 different outcomes were going to be left foot. And when we put 4 out of 16 into our calculator, it tidies up to give 1/4. The second part of this then says, what's the probability of using a red or yellow coloured spot? So again, if we look at all of our 16 outcomes, we're going to see how often do we see red or yellow. So we have red or yellow for twice in our left hand. We'll have red or yellow twice on our right hand, red or yellow twice on our left foot, and red or yellow twice on our right foot. So that means we're going to have 2, 4, 6, 8 possible outcomes that say red or yellow. So the probability of red or yellow is 8 out of the 16 outcomes, and that's the same as a half. And again, if we look at the second spinner here, I can see that red or yellow is making up half of that spinner. So the probability of red or yellow is going to be a half. And the last question that we're going to look at today, this is 2010 paper 2 question 5. So it says 2 fair coins are tossed. So I'm being told that they're fair coins. So what is the probability of getting 2 heads? So we saw this earlier where we had our biased coin, but now we're going to have the probability of 2 heads, a head and then another head. So we're going to have a half multiplied by a half, and that gives us a quarter. So the probability that the first one is a head is a half, and the probability that the second one is a head is also a half. So we multiply them and get a quarter. For part 2, it says 2 fair coins are tossed 1,000 times. How often would you expect to get 2 heads? So this time I'm not looking for a probability again, I'm looking for an answer. So what we would do here is we take the number of trials and we multiply by that probability. So we say 1,000 multiplied by a quarter, and that gives us 250 times. So if we were tossing 2 fair coins 1,000 times, we would expect 2 heads to come up 250 times. And the last part of this says, Sheila hands Porrick a fair coin and tells him to toss it 10 times. She says that if he gets 10 heads, then she will give him a prize. The first 9 tosses are all heads. How likely is it that the last toss will also be a head? Tick the correct answer and give a reason. So when you read a question like this and you're thinking, oh, he's gotten this head 9 times out of 10, it's really going to be unlikely that it's a 10 again or a head again. But what we have to look at is the fact that this is a fair coin. And when it's a fair coin, it means that the outcome of, or the probability of getting a head is going to be 1 out of the 2 outcomes, or a half, which we describe as a 50-50 chance. So a 50-50 chance means 50% probability that it happens and a 50% chance that it doesn't happen. So that's the box that we would tick here. So we would be saying that it's actually a 50-50 chance, and this is because the coin is fair. So the probability of a head is always a half. So it doesn't matter what's happened before it, and we're going to see that in next week's lesson and the following week's lesson, where we're going to see things where we have independent events. So this is something called independent events, but for now all we have to look at is that it doesn't matter what's happened beforehand, the probability isn't going to change. So that's our introduction to probability lesson, and a little bit of arrangements in there as well. So make sure to check out the 2 videos that we have made available to you as well, and hopefully that's been of some help. Thanks.